All right. Last time we were able to um, finish up to external memory manipulations, where we saw that we could read from memory or write from memory, depending on how we manipulate the control signals. This time we are going to see a more complete version of what we did last time, right? You realize that last time we were only concerned about the moving of data, but this time we are actually concerned about the execution of the whole instruction, right? So we are going to take using that single bus architecture, how the computer will execute it from scratch, right? Last time we were just only concerned about the memory operations. So here's an example. It says consider an instruction add r1. Okay, add r1 and square brackets r3. What this instruction literally means is that this is a how do you call it? It's a two address format instruction, right? And what that usually does is that the first one you see is the what destination operand, and the second one you see is the source operand, right? And now the result will be returned in the destination operand. So R1 is our destination operand, and the content in R3, the memory location in R3 is the source operand, right? So what will happen is that, and we are going to add R1 plus the content at the memory location R3 and store the results back into R1. That's what this one means, right? From instruction format. So when we have to consider it as a complete instruction, that's the PC is going to fetch it from scratch and execute it step by step. Then these are the guidelines we will follow. Usually in a question, he will give you the guidelines, right? So um be aware of that, or even if the guidelines doesn't appear, you should find your way around it. Right? You first know that you have to first fetch the instruction, fetch the operand, and execute it. So that's basically what you are doing. So the first step is that we'll fetch the instruction. The next step is we'll read the operand, that's the content of the memory location pointed by R3. As you can see, there's a square bracket around R3, which means that the address specified in the data specified in R3 is an address to another location, right? Now, we finish that. We perform the memory location, the addition, then we load the results into R1. So let's see the whole thing in code. Now, we start as this. First, we have to fetch the instruction, right? And fetching the instruction, you think about the program counter. So we will say PC out, right? Now here, the assumption is that all the registers have some out and in signals controlling them, which means that they can be allowed to write to the internal bus or read from the internal bus, depending on how you manipulate the signals. So immediately you see PC out, then the content stored in the program counter would be put on the address bus, on the internal bus, right? Now, what is stored in the program counter, it's not the instruction, it is the address of the instruction, which means that the memory address register has to take it and go and fetch that correct instruction from memory, right? So immediately you say PC out, then you say MAR in, so that you are literally transferring the address specified in the program counter into the memory address register, because the memory address register which interfaces with the external memory. Now you issue a read command. Why? You issue a read command because you are going to fetch from memory into the external bus and later put it in the internal bus, right? So you are going to issue a read command. Now you realize that here they issue select for. Why? Because um our architecture supports 4 byte instruction format one, and secondly, anytime you finish fetching from the PC, you have to increment it, right? So once we issue the PC out, remember that this bus here will now be containing the PC. Now it will flow to many places, but one of the interesting places it will flow to is that to be available at P. Once it's available at P, we want to increase the program counter, right? And to increase the program counter, it is by 4, right? So we select 4. Select 4 means that the select signal should choose the constant 4, right? So it means that A here will be 4, right? So we have PC at B and we have 4 at A. Now the result is that we'll get PC plus 4. However, remember the ALU does not store, right? So that we can get the results of this PC plus 4, so that the next cycle it can be stored back into the program counter. Then we have to activate what Zine. And remember the add signal is supposed to be specified because the ALU can do several operations, subtract, multiply, or whatever. So that's the need for the add signal. Now immediately you do that, realize that now Z will now be storing PC plus 4, right? Z will now be storing PC plus 4. But it is our mandate now to write PC back and the PC plus 4 back into PC. That's how we increase the program count, right? So you realize that the next step is actually doing that. So these two lines are actually writing the PC back, the incremented PC back into the program counter. So you first have to say Z out so that Z will put its contents on the bus. And remember, the initial PC out would disappear because you are in a new cycle. Z out Z will put its content on the bus and you say PC in, right? Now PC in would accept the content from the bus into its register, right? And just with that, we've been able to do PC is equal to PC plus 4, right? As simple as that. Now, one issue is after you've been able to do PC is equal to PC plus 4, remember the previous step we executed a read operation, right? So this read operation we executed here. Yes, now because of this read operation, we are actually waiting for the instruction we are going to fetch. The instruction was specified in PC. We put it into MAR and we executed the read operation. Now we are to wait because we are come to do something with the external memory, right? So we have to wait, right? So even though this step was supposed to just put the uh, content into the PC, we also have to wait for the memory function complete because if you don't wait and get the instruction, um, you don't wait and get the instruction you're supposed to fetch from memory, the continuous step can't happen. It's like it's dependent on this step, right? So this wait is important, right? Now, one very simple way to be able to know where to put this wait for memory function complete is usually anytime you execute a read or write instruction in the previous line, then it means that the next line you have to kind of wait for the memory function complete because you are going to use it. Now, the assumption is that after this cycle, we have waited the necessary time. So here we now have the um, instruction, right? But remember, the instruction will come and be found in the external bus because we are dealing with what external memory. So the instruction now come and found in the external bus, right? So to transfer it into the internal bus, then we have to first allow MDR to pick it, right? And once MDR pick it, so we say MDR in for the external side. Once you allow MDR to pick it, then in the same cycle, we can also say MDR out so that it will be in the internal bus. And that's what these two lines is doing. So we'll say MDR in external because the MDR is picking at the external data which was read in the previous cycles. And we have to say MDR out. So MDR out will put the data, which is the instruction actually, onto the bus, right? Now, once it puts the data onto the bus, so MDR will now put the data onto this bus. Once it puts it onto the bus, we have to decode the instruction, right? Or what we actually want to pick is an instruction. So we have to put it into the instruction register. So we have to say IR in. As simple as that, right? So with that few steps, we've been able to transfer from the program counter the instruction we needed into the instruction register. Now, once it gets into the instruction register, some is somehow to be decoded and the correct signals to be given so that the instruction can continue. But we are also looking at from the perspective of the step-by-step signals which will be given, right? But this very first four step, usually on any on any question they give you, right? Whether it is add, any question they give you, usually these first four steps will be constant, right? There's the remaining steps, right, which may change. Now remember that the remaining steps are actually what we were doing previously. The ones we were doing previously, but are not remembering the fetching of the instruction, right? So the remaining steps are actually what we were doing previously. So you realize it. So first, realize that we are supposed to add into R1, we are supposed to increase R1 by R3, right? Now, we come to the fetching of the operand. So we fetch the instruction in the first three ones. We now have to fetch the operand. Now, we have to say R3 out and MAR in. Why? R3 stores the address of an operand, the source operand actually. R3 stores the address of the source operand. So it means that we have to put that address into the MAR and allow the MAR to fetch it, right? So that's what this line is doing. So say R3 out, MAR in, then we execute read, right? Now, while we are doing that, we can't just be idle, right? But we can also say R1 out, Y in. That is, we are actually storing, yeah, so the R1 out, Y in, because we want to move the content of R1 into the Y register, right? Remember, this instruction has two source operands, right? One is R1, the other is what? One is stored in memory, right? But the address is specified in R3. Now the one in RL is easy to move into what Y in. R1 is easy to move in R to Y in, so we do that. But while we are doing that, remember that um this 5 is not dependent on this 4. That's why we can do it subsequently, right? So while we are doing that, we have to issue the wait memory function complete, because I mean after this 2 cycles, the data should be ready for us to add. Now, assuming that the data is ready, we've waited the required time, then we move to the next step. So the next step, now the data has arrived in the external bus, right? Because when you execute the wait memory function complete, the assumption is that it has now arrived in the external bus. So you say MDR in external, right? So that you pick the data from the external bus into the MDR register. Then you say MDR out, so that you export the data from the MDR register, right? You export the data from the MDR register into the internal bus. Now you realize that when it gets into the internal bus here, it can also get towards B, right? So it means that you have R1 stored in Y, and now you have the data specified by the address in R3 stored like available at B. It's not stored in B there, or you cannot store. So the next part is we select Y, so that Y would arrive what at the input A, right? So Y will arrive here, and now you execute an add instruction, right? You execute an add instruction. So immediately you execute an add instruction, you also have to execute scene. Remember, A or U cannot store, so that the results of the A or U can be stored in the register Z. Then you have to execute an add instruction, right? So now with this cycle, we've been able to add the content of R1 to the contents of the operand stored in the address specified by R3, and we've stored it in Zine. Now the last part of the instruction is now we have to what, move it back towards R1, right? So we'll have to say Z out, right, so that Z will export its data onto the bus, and we have to say R1 in, so that R will take all the data from Z, right? And we are done. So with that sequence, we have been able to execute a full instruction with this architecture, right? Now this is probably what will go on in the CPU of this architecture. The catch is that the first three lines usually will remain the same for most instructions, the first three lines, because you use the same sequence in fetching, especially if you have this architecture. But the following ones may change depending on one, the operand, two, even if it is one, the operand, and depending on how the data which you are requiring for the instruction. So just take notes. Now, another part of this is that you realize that we were really restricted in a single bus organization because you have one bus. So it was thought of that why not ensure two bus? That is, we can execute um, we don't need to one move into Y first, then later go and fetch the other instruction for the bus and add them, right? We can just do those two simultaneously, right? So that we'll be faster or we'll use smaller number of instructions, right? So the okay, so with single bus organization, the control sequences are quite long because only one data item can be transferred over the bus at a time. So yeah, some of the control sequences are really long. Then to reduce the number of steps needed, most commercial processors provide multiple internal bus. All general purpose registers are combined into a single block called the register file. The register file is said to have three ports, two input ports, allowing the contents of different registers to be accessed and have their contents placed on the buses A and B. Right. So this is what it's saying. Um, because most of the time we'll be dealing with registers, like our content will now be stored in registers before we'll do the addition or whatever operation we want. You realize that there is register file here. Right? It's just a stack of registers. This register file here has three ports, right? Two output ports, right? One for the bus A and one for the bus B, right? And so you can access the contents of two different registers at the same time, right? But you can, I think you can, it has only one input port, right? So you can write one register at a time. Then the third port allows bus C to be loaded into the third register during the same cycle. Buses A and B are used to transfer the source operand to A and B inputs of the ALU. Yeah, so you realize that one way or the other bus A is connected to the ALU, like through a MUX, and bus B is also connected to the ALU. This one is directly. The result is transferred to the destination over bus C. So what you're saying is that when you finish the operation, right, unlike the previous one where because the ALU cannot store, you first have to store in Z, then you have to use another cycle to move it back into the destination register. This one, there's also a third bus which allows you to just directly put the results in the destination register. So you have skipped that um, Z out, R in, something like that, right? The LU control signals for so if needed, the LU may simply pass one of its two inputs unmodified into bus C. This is what he's saying. He's saying that sometimes you have something in register A, you want to transfer it to register B. Now they are adding an ALU operation, which is just a transfer. So what to do is that it will just allow you to pass the content of register A, right? And that content of register A would just flow through the ALU into the Basi, then the Basi will just take it to the selected register file. So they will be using this operation to represent. So they'll say R is equal to A or R is equal to B, where R is actually the output here. So take note. Now let's see. The three bars arrangement obviates the need for registers Y and Z. Yes, I think I explained it already, right? Then another feature is the introduction of the increment unit, which is used in the increments of the PC by 4, right? So realize that in the previous one, we didn't have really have an increment unit, right? So when we wanted to increase the program counter, we have to use the same LU, right? And yeah, we have to use the CMLU and select the constant for. But now there is an incremental unit, right, which can be used for the same purpose. Now, using the incremental, it eliminates the need to add 4 to the PC using the main ALU. I think that's what I explained. Then the source for the constant 4 at the ALU input is still useful. It can be used to increment other addresses, such as memory addresses in load multiple and store multiple instruction. Yeah, so um even though we now have an incrementer that will just increase our program counter for us, we realize that this constant for is still useful. So let's not remove the multiplexer completely. Leave it there. there are certain instruction which are called load multiple and store multiple instruction, but would maybe see them in the later slides. This one, this modification will allow us to do those instructions faster. It's yes, instead of fetching from the putting a constant maybe four in a register and coming to fetch it and use it for those instructions. It is quite good because this architecture is some 4 byte architecture, right? So we can maybe use it for some arrange increment or something like that, but we'll see more of that. So we wish to use this architecture to see how we would execute this instruction. And the instruction is add into R6, R5, R4. Now you realize that in this case now, we are actually using a three format instruction, and that's an effect of the architecture, right? The architecture has three buses now, right? So it means that these two registers can be activated at the same time without affecting each other. And in fact, all of three of them, why? Because you have three separate buses for them. And that is how the organization, that's how the arrangement affects the instruction set architecture. As we stated that we should take note of earlier. So you realize that when we are to execute this one, first we have to first fetch the instruction from memory, right? So we'll say PC out. Now once we say PC out, we have to say R is equal to B. Yes, R is equal to B. Then we have to say mar in read and increment PC. Yes, so let me explain that line. Now when we say PC out, realize that the program counter is connected to the bus B, right? Now we have to say R is equal to B because we want to now the program counter come and fall here, right? But we just want to transfer it. We don't want to add anything to it or anything else because remember in the very same cycle we're incrementing the PC, right? So that the bus C will now contain the incremented PC. So what will actually happen is that the incremented PC will fall here, then it will come to B, then B will just transfer it through the OU to C, and C will store it back into the program counter, right? So that's basically it. But remember, the program counter also has the address, right? So we have to put the address into the memory address register. So we have to say MAR in. Now, we have to say a read operation because we are going to fetch from memory. So that's the necessity for the read operation, right? So inc PC will say PC, will increment PC by 4, right? And PC out will allow us to transfer into the memory address register, right? Now remember, because we have multiple bus organization, it may confuse you that some of the operation will conflict, but they will actually not conflict because you have a multiple bus organization. Now remember, because we executed a read operation here, we have to wait for memory function complete, right? We have to wait for memory function complete because the previous line contained a read operation, right? So once the read operation is ready, then we have to say MDR in external, right? Because the read operation will put it on the external bus. Then MDR out, right? And MDR out will put it on the bus B. Remember, MDR is connected to bus A and B at the same time. So you have to specify the part of the bus, right? Now we have to say R is equal to B. Yes, so R is equal to B because we want to transfer it from B to through R back into the instruction register, right? So the process of turning back into the instruction register necessitates this instruction. Then the final step, we have to say R4 out through A and R5 out through B, select A, add R6 in, and end. So this is what it means. We have to say R4 out through A because remember the register file contains a bunch of registers and they have been connected like several registers have been connected to bus A, several registers have been connected to bus B, right? But what we want to do is that we want to get the operands A and B, right? Add them and store them into what register R6. That's what the instruction says. So we have to specify, unlike the very first one where we had only one bus, we didn't have to specify, oh, put it on bus A or put it on bus B. This one we have to specify the specific bus you have to put it on. So we have to say R4 out A, which means that output um output the content in the register file for register R4, but it should be on bus A. Also output the consistent contents of the register file in register R5, but it should be on what? Bus B. So you realize that we'll now get two operands, one from bus A, right? One from bus B, right? Now you have to select A because remember, bus A fits into a multiplexer before feeding into the ALU. You have to select A. So the data flow will be something like this, right? You have to select A. And now remember, bus B is is taking register R5. Then I need to put it here, right? Now we have to issue an add instruction so that the content which are now present A and B in the ALU on the ALU input added. The output will be put into bus C, right? Now the only way register 6 can take it is by activating the L6 in signal, right? And now we can see end. So that's basically it. That's basically it. That's basically it. Now one question that may pop up is we said PC out here, and on the same cycle we're incrementing PC, right? So we had to store it in the same cycle. So wasn't that necessity for a PC in? Yeah, surely that makes necessity for a PC in signal, but um the question the answer didn't specify that, so I might find out.